So in this video, we look at more properties on the determinant. The first one is about the M and the transpose of M. I claim that the determinant of the two matrices here must be the same. Can you see why? Because, for example, if you try to obtain the determinant of M by the cofactor expansion on the row 1, and then this formula that you get is basically the same as the cofactor expansion on the column 1 for the matrix, which is the transpose of M, right? Because these are the relation between M and M transpose. And obviously, in that case, it means the determinant must be the same because the cofactor expansion doesn't depend on the rows or columns. The determinant value is not changed. And the property B is actually one of the most important one about the property of determinant. It is not that easy to prove, so I'll skip that. But just let you know the fact is that if you try to take a matrix product AB, and the determinant of such a product of AB is actually the same as the product of determinant values of A times the determinant of B. And let's illustrate it by a simple example here. So let's say now I'm giving you two matrices A, B, and we can find the determinant value pretty quickly. And we understand that the product of determinant A times determinant B is gonna be -2 times -1 is gonna be 2, right? And it is the answer to the right-hand side. Let's confirm the formula is true. Let's look at the left-hand side, which is the determinant of product of AB. And please do the matrix product here on your own. And you'll get a matrix like this for the matrix product, and you apply the determinant formula now. What you're getting is determinant 2 again, you see, so these two are the same. So it's a simple illustration to the fact that this formula is correct, and I'm claiming that this formula is always correct regardless of the size of A and B. And let's look at the next property C. So you see the fact is that if the A inverse exists, I claim that the determinant of the inverse of A is gonna be 1 over determinant A. And can you see why? Because we can look at the matrix equation. Based on definition, the product of A and inverse is gonna be identity matrix. And we can apply the determinant on both ends. And you can see the determinant of identity on the right-hand side, it must be 1, right? And we can break it down by property B here, because now the left-hand side becomes determinant A times determinant of A inverse. It is equal to 1. So it gives us the sense that determinant of A inverse must be the same as 1 over determinant A, right? And why this one must be the same here. And we can look at this theorem in a closer way based on the property C. And the theorem is basically saying that if A is invertible, which means A inverse exists, then we claim that the determinant A must be non-zero. And it is an equivalent. And let's try to make a quick proof. So let's do the forward direction first, which means I try to prove that if it's invertible, then determinant must be non-zero. But I think now it's obvious because by property C, if A inverse exists, we understand that we have the determinant of A inverse, which is 1 over determinant A. Due to this formula, obviously the determinant A in the denominator must be non-zero, right? Because we understand that this one is well defined now. So I think it means this one is obvious for the forward direction. But for the backward direction, please think a little bit more. The backward direction means you are trying to prove that if the determinant A is non-zero, we understand that A is invertible. So maybe for some of you it looks obvious, but I would try to be slightly more careful here. To prove this statement is correct, equivalently, we can try to prove that if A is not invertible, then determinant A is 0. So I'm using the fact that the two logical statements here are the same. A implies B, which is this one, is equivalent to the statement not B implies not A. And I believe quite a lot of you have seen this kind of logical statement. But anyway, if A is invertible, what does it mean? So please recall in the previous video, we have learned how to find the A inverse by using the row operation method, which is like this. You can list the two matrices together, A and identity, and by some row operation, you have to do it yourself. You have to try your best to make the left-hand side identity, and then automatically the right-hand side is going to be A inverse. But now we are assuming A is not invertible, so it means that most likely what we are getting is we are not able to reduce the left-hand side to a matrix which is identity. We are not able to do it, and it means we actually totally zero rows. And you can try to do it yourself. And totally zero rows basically means determinant must be 0, right? And based on the previous video on the properties of determinants, we understand that by the property 11, we understand this kind of row operation does not change the determinant. It basically means, because we know that the reduced form has determinant 0, it means the original matrix must have determinant A equals 0, right? Because we expect the determinant 0 is not changed. If you reverse the row operation to get back the original matrix, and it shows us that we expect that the determinant A is 0. And you can see my explanation is a little bit imprecise here, but I hope you can roughly understand the idea here. And that's the end of this video.